Okay, so today I'm going to be talking about browser exploitation, the cool stuff about the browser exploitation actually that happened in the past, right now, and reinventing ideas, sharing some sort of the research that I was doing along with other cybersecurity guys from Google research team, and debugging the exploit kits, trying to inspect the delivery methods for these kind of exploit kit. So it has actually two parts. The one part like is technical, the second one is scary. And we're gonna see how it goes. So who am I? My name is Jameel Nabbo. I work for Ingram Macro as a security consultant. I have a cool website called bufferoverflows.net. Check it out. So web browser, it's very interesting. It's a sport for the security researchers actually, as well as the cyber criminals, right? And some stuff that I will be talking about today that is not developed by individuals, developed by highly skilled guys like research institutions and stuff for doing crime. And why it's interesting, anyone is using browser, anyone using the internet is using browser. So yeah, this talk is not about dumb tree exploitation. These are bullshit, sorry. So I'm gonna jump over. If we're gonna exploit the web browser, how do we start? Yeah, we actually got a lot of methodologies to apply to this. The first one, we can go ahead with WASM. WASM wasn't exist a decade ago. So right now we have WebAssembly. This is what WASM is. JavaScript core, browser engine, old-fashioned, and the unknown. And to unknown, I'm referring to some sort of environment exploitation that is, not known yet, maybe in a heap spray. So the old-fashioned was starting by Java drive-by. This is the most popular one. We got Java. Actually, there's Java drive-by and silent Java drive-by, which was really common in the browser exploitation technique because it's across the platform. It works very simple. It's easy to develop that exploits. It's easy to debug. The Java code is open source. Oracle guys, after Sun Microsystem, it got by Oracle. So there was a lot of stuff happening in that move, especially in the exploit development. So the other Flash applier, this is Microsoft Silverlight, the ActiveX for the Internet Explorer. Exploit kits, so we got Black Hole, we got Angular, Nuclear Magnitude, these kind of cool guys. They have a fancy logo, they just put their names. If you really dig into the exploit case and the crime history, you're going to find really, as Malware Byte says, the king of exploit kit is Black Hole. Why? Because it uses really cool delivery techniques. If we say about executing a malware, like there is hackform.net and these spot for dark web and the cybercrime. You pay $10 and you get a malware actually encrypted, full undetectable, bypassing the UAC, user access control for Microsoft, I think, KCLR, ACLR, these kind of stuff. Actually, when you have the binary or the malware, it's really not that complicated to run it on the system. But the idea is, or the complexity is to deliver it throughout the browser. And we got a lot of delivery technique within the browser, like if we talk about the past, like the cross-platform one, and so on. So when Black Hole is dead, actually we got Angular, and Angular it's used very advanced enumeration technique. I'm not gonna analyze all of the stuff, only the stuff that is related to the topic. So it's used like Internet Explorer, Flash Player, Adobe Reader, zero-day exploit packed. Now, the cool enumeration technique that is used in Angular, because when an Angular is started, this is what I'm reading in the news, it was actually targeting high individual profile. And we got two stages of enumeration. The first stage is to enumerate, of course, the user engine, the version, the running operating system, and these kind of stuff. And then if it's like Internet Explorer 8, 9, 10, so it goes ahead and, it runs this CVE, which is recently discovered. Basically, it's an exploit within the XML parser, within the Internet Explorer. Exploiting it is very basic. You just supply a file that exists on that system. And when this trying to parse the XML, trying to parse that XML element, so it actually gives an error messages. That's how they know that that file exists on the system or not. So based on the error messages. But on the other hand, it got improved like development when they used the REST protocol, which is they was actually supplying the local host, which point out into the root directory in the Windows system, talking about Windows 86. So this will print out the content or the files within the directory. So what you get actually, you get these kind of stuff, dummies, hard to read, but it was actually used to enumerate if there is Kaspersky installed, image tool, the Microsoft exploit multigation tool, and these kind of stuff, because they have no control after running the exploit. So that's why they use the enumeration part, which is, I think it's a bit advanced. So yeah, they basically supplied some sort of vendors, if these vendors exist. So they do a different type of exploitation. But this was the cool enumeration technique. And why they use this kind of technique? I mean, what is the purpose? It's very simple. When we get an analyst, like someone supplied this into VirusTool or these kind of stuff, so an analyst get a nightmare and he try to figure out what is the malware is and how things is working. And basically they know some file that exists on the analyst PC, and then they try to make a play around. Use after free. If you talk about the web browser, you're going to go ahead with use after free, heap spray, and a lot of stuff. And myself, I love Pony, guys. So Pony, use after free. It's always been exist. Till now, it's exists. So you're going to find it even in the future, 10 years later, if we stay alive. So it's really popular. The heap spraying attacks and these kind of use after free. In simple terms, I'm not going to like dig into it. We are like if we say there is a developer that made an application, so basically he allocates, so it's a design error, right? So he used a pointer called dangling pointer. In computer science, we have dangling pointer, wild pointer. These point to invalid memory address or object, and when that area of memory is freed, so the attacker goes and reuse that memory area. They call it code reuse as well. So we got a block A, block B. Block A is freed. Block B is controlled by the attacker. He used the previous allocated block, and he tried to execute code. If you research about UAF attacks, you're gonna find like memory leaks, this kind of stuff. But it is mainly used for code execution because nothing to do with the memory address. This is a quick example. Pointer pointing to an malloc. Freed, reused, get the memory. So 4 years of happy UAF in Firefox and SeaMonkey, and it was from 2007 till 2011. And if you really go until now, it's in some sort of UAF exploitation still exists. If you go there, they use like they say disable JavaScript. If you really follow the Twitter tweets of the guy, they say okay, don't use Firefox also. So in simple terms, how it works. I'm going to show you the POC, but in simple terms, like it's we initiating a fake v table, and this v table will point to a PSTR, which is in the Windows kernel. PSTR means binary string. It's a D word, D double word, 2 bytes. So double is 4 byte. Each byte is 80-bit. And 32-bit we got. So then the allocation for the heap start, and we're filling it with a new shellcode. So it's a really vanilla. If you can read my screen, you're going to find there is an object. This is how it works. There is an object, and this object, we call it using a foo. After calling it, we're creating some Unicode. That's why we use an escape over here, and then a shellcode to pop up calculator, and then do the heap spray. How the heap spray works, basically just sort of string. Just create a string variable in JavaScript if you want to play with the heap or the virtual memory, and then you assign some sort of junky value to that string, and then you add that string to himself, and then you subtract that string. So that's how it works. So we're creating 1,000 fake allocation, and this is how it works. Now, the scary part, Snowman was in operation. I don't know if you heard about it, but it was targeting really high individual profile, targeting United States military guys and guys in French, research institutions, and etc. mainly was working for Windows Internet Explorer 10. These, without diving into the politics, but the really cool technique about this exploit, which is published by FireEye, it's the delivery. This is the cool technique. So basically, a victim visit an HTML web page, a server reply with an iframe. The iframe connect to the server again, and then it call an img.html, which is, on the other hand, place an SWF file that has an action script. This is where the exploit is. And that the SWF file actually go ahead and try to fetch Erdo GPG image. That image is not placed on the file system memory. On the file system, it's placed in the memory as an array buffer. So it's like an aviation technique. And then it's dropped in DLL with a TXT file, and that DLL read from that TXT file. And it's a second stage, and then it's run the shell code, which is connect back in a reverse connection. So in very simple way, we got the URL loader, which makes an internal request. This is a snapshot that I took it. And then we got the array buffer initialized, and then the underscore URL, which is hold the name for the JPEG file. This is returned into a loader, and that loader returned into the memory, and it gets executed. So it's a buffer array executed within the memory, so nothing placed on the file system. Adobe Flash, I'm not going to talk a lot about it. So Rhino Java drive-by. So I mean Java drive-by exploit is very popular. So I have no other space over here, just only for 1 year. The Rhino is basically a Java script engine written in Java, which basically you can implement JavaScript calls and this kind of dumb stuff into the Java itself, and then you build a communication channel. But it had a bug in its design where you can initialize a script engine, and you call the JavaScript engine, and then after that you bind it into an applet. At the top, it's extend an applet. So you bind into an applet, then you pass an object, and when this object is passed, you actually return an error object. So basically, it's a native error class. That native error class uses a toString method. That toString method is not controlled, which is you get like, there is no context association with the current thread. Basically, it's a runnable object, so it runs in the thread, and that's simply you just place instead of Metasploit, you place the stuff that you want to be executed in Java. Now, I'm gonna go ahead with no one will do it, I think, but I don't have SSH. So I just built an application in assembly. That's a fully functional web application that I can give instruction into the browser. And this code runs without a decoding or something. This code runs in native way, native. So if we're gonna check it out, sorry. And I was talking. No cheat. So basically, it's an assembly application. We got some sort of binding section that checks in have some sort of text, and then we're doing some assembly calls to instruct the web browser in order to put these and manage these stuff. The listener for the HTTP, the protocol, some assembly instruction manually written. Right now, We got an O, output it as an app, run it, it's running, go ahead. So yeah, we got some sort of functionality going on. If you inspect the source code, there's no cheat, there's nothing like with the JavaScript. It's mainly based in assembly. But on the other hand now, if I talk about, I want to fuzz the browser, for example, or write a native assembly code, this is really a pain, right? So that's why we got a fancy stuff called WebAssembly, which is basically, it's not an assembly. It's basically has its own textual structure, which is not an assembly. But the difference between the assembly, the WebAssembly actually, and the JavaScript, because we already have the JavaScript, is the WebAssembly is a compiler target. Okay. So the WebAssembly is a compiler target. It's faster than JavaScript. Yeah, it's run a code. It's run actually close to native, not native, close to native. And then it's executes C++ code. And what does it bring to the table is speed, portability, flexibility, these kind of stuff. Yeah, here you can see that the JavaScript code need to be parsed and then compile, optimize, then execute. Only the WASM code need to be decoded and compiled. And if you follow the current modern zero-day right now, I mean the one that are published, you're going to find that it's written in the assembly modules, and the WASM modules specifically in the import and export. So all the browsers right now support it. And the cool part, you can write a JavaScript by calling assembly functions. So this is the difference between the normal assembly that we know and the textual format of the WASM and how the binary format. So the WASM binary structure, we got type, import, function, table, memory, global, export, start, element code, and each one of them is a separate topic. But we got the custom section, which is this is where the vulnerability started with the WASM parser. A custom section means that the section does not exist over here, and that is past the checks. So basically, WASM had a problem with the verification of the order of these sections. So in the C code, yeah, this place there is a validate order, and this is if the previous section is a custom section, return true, and it's passed. So it was actually a design error. I'm not going to talk about these, just wrapping up. WebAssembly, yeah, if you build an application using WebAssembly, you can have two methods for delivery. One is downloading a file, the second one on the fly. On the fly has exploits also. And this is why the on the fly is faster, and also it's faster for the stagers. WASM parser exploitation, we got some sort of functions within the parser itself. And if you really read up the code, you're going to end up with a lot of heap stuff and UAF. This is one example of them. We got a function called getWASM buffer from value. And this function actually takes a data view, array of buffer, and it has a vector. And then this is passed to another function, which means we right now have a buffer twice is copied. We got out of bound read. And we get a memory copy out of it. This is how the POC look like. Passing a data view, loading it into WebAssembly module after creating some fake loops. And we get type confusion with buffer overflow. Now I'm going to perform a live demo, quick live demo about using WASM in exploitation. This exploit is made up by the workers. Why the workers used over here? It's because these workers runs in, sorry. yeah, these workers run in their own thread. So basically, we're defining some constants, the allocation for the spray holders, reclaiming, finding the patterns, going out very quick. So yeah, the reading addresses, the writing addresses, the corruption table, the reading objects, cleaning up, getting the freed memory, the shell code, and yeah, how the RSC is working. Basically, this is the spot that I want to talk about. We have a WASM converted into hex, and this is loaded into inside integer array. And after loading it, we're creating an anonymous, and we're passing anonymous definition for a WASM module, loading the code that we defined over here, and an import object. Then we return this as an export function, which it's gonna run in a WASM file. Right after that, we do some loop on the shell code. We verify some stuff. The post meshes over here is not an HTTP post meshes. It's more about the worker itself. So we basically pass the worker is a thread, and we pass a process to that thread. So it got run in its own thread. And initialization, we trigger the free into a try block catch. We try to find the information in the log. It's like a huge exploit, but let's see it in action. This exploit, I hosted it on my, I'm using Google Chrome right now. My system is patched, everything is cool. And I hosted it on my website. I hope it works. It's gonna brute force for the making some attempt for the allocation on the buffer. Gonna take some time for brute forcing. It's brute forcing, and we got the calculator. WASM is really dangerous. Moving on, we got the love story between SMGS and just-in-time compiler. And basically, it's the same idea for the heap spray of the Flash player, the guy who came with this kind of exploitation. Actually, it's really cool because it doesn't use any code reuse. So there's basically no brute force, nothing is going on. So yeah, just to see it in action very quick. A piece of junk. Virtual allocation, read, write, execute. 3 byte stager, and the virtual memory. Right after that, we got an MSF Venom encoded to SMGS payload. We are getting some, the fake objects, moving about the blocks, creating this allocation, getting the addresses, triggering the worker, same technique, using the back-end thread, and then passing the process, getting the offset, looping over the blocks, triggering it by creating fake SVG, doing some sort of animation in order to allocate some sort of memory stuff. Now trying to, I hope it works. Okay. And we got the CMD instead of the calculator. Moving on. Okay. Yeah, it's the same one that I see here, right? So yeah, the techniques for delivering the web browser exploit, it's basically when I actually was entering into this, everyone telling me, don't click a link, don't click a link. So I was really afraid, but right now it's I think it's true. We got a lot of social engineering techniques that has been delivered. One cool thing about them is to enumerate the system. And before enumerating the system, actually, what they do, they create a pixel, 1 pixel image, right? So they host this image on any kind of server. And when you go to your Gmail account in order to insert an image from a URL, What you give on the server side, you retain a base64 GIF. So if the Google bot is requesting that image, that's how you insert an image into your Gmail browser. It's going to go fetch that. And on the other hand, when a request happens on the server side, you grab that request. So who requested that image? So you get the request data. Outlook sometimes blocks the image, loading image from external sites. But to be honest, when you load an image from external site, it's really a problem. It's not only about enumerating the system. Now, if you, in my research, and you can find this information documented, these guys load an iframe by default, so they don't block it. What means is that you send an email to the victim, right? And then you inject an iframe to your payload. And when this gets executed, it's going to be executed within the email. And what the email use? Yeah, just Google what the browser engine each email, one of them is using. So I think this is the next generation for the exploit kit. The hidden part, my research, no one is mentioning this is the black hole for web browser exploitation. No one is writing about it. Mainly the DOM tree exploitation, like XSS, these stuff, ISO type of exploitation. But on the other hand, you can set an item, get an item, remove item, clear. This where this happens in the browser local storage. In 2018, I did the research that I was able to create an exploit that places a string shellcode into the browser storage. But the only missing part that I had, how I can trigger that payload without going to execute something else. The problem that I had, actually, what I did, I created an exploit.js, which is, it's very basic. It's to store some sort of shell code that is, it get it from a target.exe, which is like a calculator. And then it set an item within that, the local storage, and then we get that item. But how, the problem is on the browser, we got a lot of limitations, actually. This is beyond like buffer overflow attacks. Is how I can let the browser read that shellcode and getting it executed. I can't make the browser read that, but how I can get it executed. So I created an extractor, and when I run that extractor, it's gonna go grab the string within the browser and get it executed. So this was the only missing part, but it's still ongoing research. WebAssembly is still ongoing. You're going to find a lot of bugs if you do static analysis. This is only the things that I can show to you in 30-minute talk. The conclusion, browser exploitation basically is a science in its own. So it's the most complex topic in a binary exploitation. But the sources that I really found handy in order to enter this space is the exploit DB POC, the Google research team, the binary exploitation debugging for Corlan. If you do an OSEE, it's really cool. These are the credits for the guys, the references, and me and Pony, if you got questions. So that's pretty much it.
Thank you, Jameel. Awesome. Yeah, I'm sure people will have questions for you in the break. We're going to have a quick break.
Oh,
but do you
time.
Okay. Do you have a website that you can point people to for examples in your blog and whatever?
Yeah, these materials will be published. So you're going to find it on Secti and on bufferoverflows.net, where I post stuff about research, scientific research. Recently was doing research in the compiler design, programming language design, how we can find exploit in that. So you can find a lot of cool stuff over there.
Cool. So thanks again, Jameel.